Hello, so we have talked about how we can solve the logistic model. We've talked about how we can solve the logistic model using, first of all, by phase portraits. Okay, phase portraits. Phase portraits. Okay, then we talked about how we could solve it. We looked at another approach of how we could solve the logistic model. We talked about linearization. Okay, so in other words, we find the equilibrium points. Okay, so the phase portraits, we just basically, try to draw a picture and try to look at what was happening around the equilibrium points, and kind of could then use that information to look at, kind of try and sketch then a graph that could look like the look like the logistic model. But we had no idea what the solution to the logistic model actually was. All right, so in other words, what the formula for the population actually was. Okay, then we looked at the linearization model, which effectively, again, we found the equilibrium points just sort of by inspection, a little bit of algebra maybe. Again, nothing too difficult, and then could kind of tell the stability and and things like that just based on logic, the process behind linearization and kind of the general rules behind linearization. Basically, it came to the derivative of a function at the equilibrium point. If that was greater than 0, then that led to the equilibrium point must be if it was greater than 0, it must be unstable. Okay, and likewise, if we had the same thing, but this time where the derivative of the function evaluated the equilibrium point was less than 0, then that must mean the equilibrium point was asymptotically stable. Stable. Okay, so we could use linearization to determine the stability that way. But now what we're going to do in this video is we're going to actually just jump in and we're going to actually solve the ODE. Okay, we're going to show you how. I'm going to show you how we can solve the ODE. We're going to come up with an actual answer for what the answer, what the function of the logistic model that satisfies, what the function of the population for the logistic model actually is. So in other words, here's the logistic model. So we had dm by dt, okay, equals Rn, which of course was the exponential model, but then we multiplied it by 1 minus n on k to take into account that actually the population should level off after a period of time. So in other words, what we're going to do in this video is actually come up with what the formula for this function n is, so what n equals. Okay, and that's kind of the idea behind this video here. So first things first, we got dn by dt equals Rn times 1 minus n on k. I must warn you, there's a lot of algebra in this video, but it's kind of just it's not difficult algebra, and I really encourage you to go through it yourself. First things first, I've got brackets. Now, whenever you see a bracket inside in an equation, I always encourage you to get rid of them, because they're a bit like barriers, okay, and they kind of obstruct you, helps in your thinking. Sometimes they can help you kind of partition or group together bits that you might come to later on, but for the moment, they're a barrier. I need to work with it, so therefore I'm going to expand the barriers out. So, those barriers out, the brackets out. So you end up with Rn, so I'm just going to multiply through by Rn minus Rn squared on k. Okay. Now the next thing is, I look at that now, and whenever I see a fraction, I always try and get rid of it. Okay, and the way we should get rid of it is just multiplying through by k in this case. So I end up with k dn by dt, so I have to multiply every term by k, equals k Rn, and I'm going to write it, so k times Rn minus Rn squared, because of course I multiply by 3 by k, and that was the aim. I was trying to get rid of this fraction, multiply 3 by k, they just go away. Okay, so this is kind of what I'm left with now, and the idea is then I want to try and solve that. So I can actually just factorise this right hand side just by taking an Rn out now. Taking an Rn out, so I end up with, what am I left with? K minus n. Yep. So k times the derivative of my population with respect to t. K times my population with respect to t is equal to Rn times k minus n. That's what I'm left with, and I want to try and find n effectively. Well, look, I know what the equilibrium points are for this function. I've shown you in the linearization case, but in case you're not sure, effectively I just look at this. I know that an equilibrium point must be dn by dt equals 0. I must know that the derivative is equal to 0. That's where an equilibrium point must exist. So therefore that implies that Rn times 1 minus n on k must be equal to 0. So therefore that implies that either Rn equals 0. Well, I know that R can't be equal to 0 because that's a growth rate. Either grows or it, either the population either grows or it decays. It can't very rarely stays the same. It has to change effectively. So r can't be equal to 0, so therefore n must be equal to 0. And likewise, I can look at this thing, so 1 minus n on k equals 0, okay, and that implies that, you know, n on k equals 1, multiply 3 by k, okay, so I get n equals k, so that's my other equilibrium point, n equals k. Okay, so those are my two equilibrium points now. So I know those are my two equilibrium points. Okay, so let us assume that for when n is not equal to either of these two values, so when n is not either equal to 0 or k, when it's not equal to them, then we can obviously solve this ODE effectively, and we can solve it by a technique called separation of variables. And the idea is that basically we get everything which is involving, well, we look at this first of all, this derivative, okay, this dn by dt, and we try and get everything which involves n, so we get everything which involves the numerator, which is dn, so everything which involves n on one side, and everything which involves the denominator, which is in this case dt, so everything involving t on the other side, or a constant on the other side. Okay, if possible. We're not really worried about where the constants end up, but you know. So basically what we're going to try and do, is get everything involving n on one side, okay, and everything not involving n on the other side. So effectively what we end up with, this k is fine, it's just a constant, okay, times dn, okay, and then if we just divide through by n, so this is rn k minus n, so I'll just write it out again, just so you guys can see. So first of all, I'm going to divide through by n, to get this k on n, okay. I've got a k minus n here though. Well, that's fine, because this is a constant minus n, okay, so it's not involving t, so therefore I'm also going to divide through by k minus n as well. So actually I'm going to divide through by n times k minus n, okay, on this side, so therefore that gets rid of that. And then I'm just going to multiply through by dt to get the dt on that side, okay, and then I can just integrate both sides quite nicely. Okay, so this is just what I end up with here, alright. So, first things first, I'm going to look at, well, this is fairly easy. This right-hand side is easy because it's just I'm treating r as a constant, right? So r is a constant, and I'm integrating with respect to t, so therefore the answer is going to be RT, and it's going to be plus some constant of integration. Okay, so RT plus some constant integration. This left-hand side is going to be slightly trickier, because I'm going to have to basically use partial fractions, okay, because I've got k over n times k minus n, okay? So I've got something on the top, and then I've got two things multiplied by each other on the bottom. I want to split those two things up. Okay, so the way that I'm going to do that is by partial fractions. So I'm going to say that, okay, you know, I can write it as some fraction. I can write this k over n times k minus n as a over n plus b over k minus n over k minus n. Okay, so then what I'm just going to do is just going to multiply through by k minus n. Okay, so I'm going to end up with here I'm going to end up with a lots of k minus n. Okay, it's just algebra, plus b, and I'm going to multiply this by n, so bn. Okay, so then what do I get on the bottom? I get a common fraction effectively, d lots of k minus n. Okay, what's going on there? That's a k minus n, okay, and that's equal to k lots of n times k minus n. All right, so then effectively I can just consider the numerators now, because you know, if I just multiply through by n lots of k minus n, I just get rid of that. So effectively what I'm saying is that k is equal to a lots of k minus n plus bn. Okay, right, okay. So first of all, I'm just going to choose a value for n, effectively, to try and kind of get rid of some stuff. So first of all, I'm going to let n equal k. I'm going to let n equal k. So what happens if I let n equal k? I'm going to get k equals a times k minus k plus bk. Okay, so therefore this just goes to 0. This k minus k goes to 0, so therefore I get rid of that. So therefore that implies that when n equals k, k equals bk, so therefore b must equal 1. Yeah, because I just divide through by k, I just get 1. Okay, so just by choosing a value. Okay, so I now know that b equals 1. Can I be clever again? Well, yes, so now I know that b equals 1, I can just sub that back into my thing. So I get k equals a lots of k minus n, okay, plus b, which I now know is 1 times n, yeah? So I just end up with that, okay? So if I now take this n over to the other side, I end up with k minus n equals a times k minus n, okay? Then I just divide through by k minus n, okay? So this just k minus n over k minus n just cancels to 1. So therefore I get a equals 1. So I end up with a equals 1 and b equals 1 as well. So if I take it back to here, I can just now rewrite this as 1 plus, and this is 1 as well. Okay, so in other words, I can now rewrite my integral, this integral here, as, I'll just write it up down here. I'll just write it as the integral of 1 over n plus 1 over k minus n with respect to n. Okay, and I've just worked out what the right hand side was. It was rt plus c. Yeah. So effectively, all I've just done is just taken this thing here. I've split this integral, or this integrand, supposedly, you know, the thing which I'm integrating is called an integrand. So I'm just split that up into using partial fractions. Okay, I've worked out this right hand side already. And I've just rewritten it down there. That's all I've done. Okay, so now I can just integrate it directly. So this is 1 over n integrated with respect to n. Well, that's the natural logarithm of n, right? And then this thing here is almost the natural logarithm, because I've just got a constant here, except for this minus. You remember that a natural logarithm, you know, the integral of a function differentiated over a function with respect to x is just the logarithm of the function. Okay, that's kind of the general rule which we end up with. Well, this is very almost that, except that the derivative of my denominator would be, with respect to n, would be minus 1. Well, I've only got a 1 on the top. So in other words, what I'm going to have to do is be a little bit clever and basically put, change, you know, this to a minus and put a minus there, because then effectively, you know, I'll end up with a minus times a minus, which becomes a positive anyway. Okay, so now what I'll end up with is minus, and now this is now exactly what I want. It's just the logarithm of what's on the bottom, so k minus n. That's just you know, first year calculus effectively, equals rt plus c. All right. So now I end up with that. Well, I can just use my logarithm laws. I've got two logarithms to the same base, e, being subtracted. So therefore I can just divide whatever's inside, you know, the bracket. So ln of n over, k minus n. Okay, so that left-hand side reduces to that. Okay, equals rt plus c. Okay, so I just rewrite this. So this is basically saying e to the power of this equals that. Okay, so I can just write that. So e to the power of rt plus c equals n over k minus n. All right. So what can I do there? Well, this is still a modulus, by the way. So I can say then that this here is actually equal to e to the rt times e to the c, because if you look, I've got two things to the same base. Okay, when I've got two things to the same base being multiplied together, I just add the powers, so therefore I get this back. So I've just now done it in reverse almost. Just split it up again, and I'm just going to let this is just going to be e, which of course is just a number, raised to some constant, which is just a number. So a number to a number, that's still going to be a constant, right? I'm just going to call that constant a. Okay, so it's going to be a e to the rt. A e to the rt. All right. Now, let's introduce some initial conditions. Let's suppose that the value of our function, so the value of our population at time 0, okay, we're just going to denote that by n naught. Okay, so this is just saying that, you know, at time 0, so we consider a point in time where we start looking at our population, and at the very start of the population, we're going to have, you know, the number of people in our population is going to be called n0. Okay, so in other words, when t equals 0, this is the case. So we end up with, what have we got? We've got n over k minus n, okay, is equal to a e to the rt. So when we put t equals 0 into this, so just place t by 0, well, look what we end up with here. It will be, what will we end up with? This is just going to be 1 now, because it's e to the power of 0 effectively. E to the power of 0, it's just 1, okay? And we know that that must be equal to No, that must be equal to 0. This must be subscript 0. So this is n0 now. Okay, because when we put t into this thing, our n goes to n0. So we put t into this thing, we get 1 here, okay, and I can just now replace my n's by n0s. Okay, so now I know that my a, my constant, is n0 over k minus n0. Let me just show you that very, very quickly again, because I don't think I explained it in quite the right way. So n over, just in case you missed it, k minus n is equal to a e to the rt. Okay, so now I know that t equals 0, so I can replace t equals 0. That's what that means. T equals 0 into this, so when I place 0 here, okay, I get 0 here, and I also replace n by n0. N by n0, okay. Well, this here, e to the 0, goes to 1, so then I'm just left with a equals n0 over k minus n0. Okay, so let's just consider what I had. So I now just replace this a in here, so I end up with n over k minus n is equal to a, which is n0 over k minus n0, okay, e to the rt. Yep, okay, that's all cool. Now we know that effectively, you know, we can effectively just get rid of these modulus brackets now. We didn't, strictly speaking, if we wanted to consider it thoroughly, then we should have considered it. But, I mean, I'm not going to take you through why we can just get rid of them, but we can just get rid of them. Effectively, it just means that we just have a positive population. We can't have a negative population. Okay? So, therefore, what do I end up with? I end up with n equals k minus n is equal to n naught e to the rt over k minus n naught. Okay? So now if I just multiply through by k minus n to just get n on its own, so basically what I'm trying to do now is just get n on, you know, get everything in terms of n, make n the subject of the formula. So making n the subject of this formula, what do I end up with? Well, I get n equals, what do I end up with? M naught e to the rt, okay, over k minus n naught, okay, and that's all multiplied by k minus n now. Yep. So now if I multiply this by k, I get n naught e to the rt over k minus n naught, okay, times k. So times k, and I'm going to write k out the front there, okay, minus, now this all, you know, with respect to, this all multiplied by n, so I get n multiplied by n naught e to the rt over k minus n naught. Okay, I'm going to take this now. Over to the right hand side. This second term over to the right hand side. So what I end up with is n plus n times n naught e to the rt over k minus n naught. Okay, and that's all equal to k n naught e to the rt over k minus n naught. Okay, this is just, basically what I'm just doing is making n the subject of the formula, okay? I can now factor out an n on this left-hand side, so I end up with n times 1 plus n naught e to the rt over k minus n naught, okay? And that's all equal to k n naught e to the rt over k minus n naught, okay? And then if I just then divide through by this thing here, I'll just get n on its own. So n equals k n naught e to the rt over k minus n naught, okay, divided by this thing, divided by all of this thing, which is the same as multiplying by its reciprocal, right? So I'm going to just multiply by its reciprocal. So multiplied by 1 over 1 plus n naught e to the rt over k minus n naught, okay? And then basically I can just multiply tops and bottoms together, it's just a fraction. So I end up with k n naught e to the rt, okay, over k minus n naught, okay, multiply this through by the bottom, so k minus n naught plus k minus n naught times, my word, n naught e to the rt over k minus n naught. This is nasty. Okay, I'm just going to make the bottom, this bottom into one fraction, effectively, just by multiplying this term by k minus n naught over k minus n naught. So I end up with k n naught e to the rt over, this is k minus n naught squared effectively, plus k minus n naught times n naught e to the rt, okay, over k minus n naught. Okay, so now what we'll end up with is just this thing. I can now say that this is that's divided by that, so therefore that's the same as k n naught e to the rt times k minus n naught over k minus n naught squared plus, this is a lot of work, plus minus n naught. Okay, this is n naught e to the rt. Right, okay, so now let's do a little bit more work with this. This is a nightmare. So I'm going to now take k minus n naught out of this bottom here. So I'm going to end up with k n naught e to the rt times k minus n naught over k minus n naught times k minus n naught plus n naught e to the rt. Right, okay. Oops, square bracket. So those two things cancel. Yay, that's good. So that's equals now. Go away, go away, go away. Equals. This is k m naught e to the rt. Oh my word. This is k minus n naught plus n naught e to the rt. Right, okay, so this is k minus n naught plus n naught plus e to the rt. Let's take out the n naught now. K n naught e to the rt over, this is what we got. We got n naught, lots of e to the rt minus 1 plus k. Can cancel the n naughts off. Yeah. So what we're left with, k e to the rt. I hope this is right. Do you know what? Actually, I'm going to stop. I'm going to get rid of all of this. I think, you know, you can carry on going over and over and over again, but I'm just going to actually just leave it like this. Going to leave it like this. So this is my, I'm just going to say this is my exact solution. I don't know how that got there. Let's get rid of that. There we go. Yeah, so this is, I'm going to say my exact solution now. Okay, and actually what I'm going to do is I'm going to multiply through by e to the rt, e to the minus rt. So multiply tops and bottoms by e to the rt. I end up with, just to get rid of that thing there, and, you know, make it just look a little bit nicer. So I get k n naught, I'm going to multiply e to the rt times e to the minus rt on the top, and this thing on the bottom, so I end up with k minus n naught, okay, e to the minus rt here, plus n naught e to the rt times e to the minus rt here. Those two things cancel, okay, and therefore I've written it in a slightly neater way. So I'm going to say that's my final solution, and I'm going to leave it well alone. So that is my final solution to the logistic equation. Oh my word, that was a lot of algebra. I really encourage you, like I say, you know, thing is, it looks worse than it is, okay, with algebra. There's a lot of algebra there. Go through it, do it yourself, and kind of have a look and see what happens. So let's try and draw and see what this graph actually looks like. You know, you do it yourself. You plug it into Google or whatever, and it will probably do it for you. But effectively, or plug it into Maple or something like that. So this is N, this is T, okay, and this is my carrying capacity here. Okay, and when I kind of do things, basically the idea is that I want to try and approach this carrying capacity at all times. So kind of do this kind of thing. Okay, if I'm below the carrying capacity, I'll basically do this kind of thing. Okay, so approach the carrying capacity. If my population somehow manages to be above the carrying capacity, which again is kind of impossible, basically the idea is that, you know, this graph here, this top graph here, the idea is that it always try and approach the carrying capacity. It just shows that, you know, this is asymptotically stable. It approaches it from both sides. Okay, if we vary n naught, all that basically means is that we just start at a different value, but it's going to follow exactly the same shape. Okay. Now, what happens if we vary? What happens if we vary the growth rate? What happens if we vary the growth rate? So this is just n. This is t. Okay. So this is just different values of n naught. So this is n naught. This is n naught. It's just different values of n naught. Say. Okay. Now, what happens if we vary the growth rate? Well, here's our carrying capacity. Yeah. So the reason why we consider this thing up here is if we considered a sort of a initial population that was, say, up here, for example, and it was greater than the carrying capacity, then the idea is it will always approach the carrying capacity. Okay, let's just have a look at this. Well, it's going to follow exactly, so fixing n naught, so we're starting at the same value, it will always try and approach the carrying capacity in this kind of particular way, but just by changing the value of our growth rate, it just means that it will approach this carrying capacity at a faster or slower rate. Yeah, so it's going to follow exactly the same, you know, say if this was my first growth rate, second growth rate, third growth rate, my first growth rate is bigger than my second growth rate, and my second growth rate is bigger than my third growth rate. So in other words, you know, by increasing the value of r, it just means that we're going to reach the carrying capacity at a much faster rate. It's also to remember that for a really small population relative to a carrying capacity, so say for example, if we've got a really small population relative to the carrying capacity, then the actual growth rate of the population is close to the linear growth rate. So in other words, you know, this kind of thing, this linear growth rate is going to grow in a linear way if our population is small enough compared to the carrying capacity. Okay, so that's kind of, you know, that's a useful thing which can be remembered, and you can actually exploit it in order to estimate the linear growth rate in a population modelled by the logistic, growth rate logistic model. Okay, so hopefully that makes a bit of sense.